Welcome to the Scientific Sense podcast, where we explore emerging ideas from science, policy, economics, and technology. My name is Gil Eapen. We talk with world's leading academics and experts about their recent research or general areas of topical interest. Scientific Sense is an unstructured conversation with no agenda or preparation. We cover a wide variety of domains where new discoveries are made and new technologies are developed on a daily basis. We are most interested in how new ideas affect society and help educate the world how to pursue a rewarding and enjoyable life rooted in science, logic, and information. We seek knowledge without boundaries or constraints and provide unedited content of conversations with researchers and leaders who love what they do. A companion blog to this podcast can be found at scientificsense.com, and this podcast is available on over a dozen platforms and directly at scientificsense.net. If you have suggestions for topics, guests, and other ideas, please send them to info@scientificsense.com, and I can be reached at gil@eapen.info. My guest today is Professor Sean Smith, who's a professor of Computational Nanomaterials Science and Technology at the Australian National University and Director of Australia's National Supercomputing Facility, NCI Australia. He has extensive theoretical and computational research experience in chemistry, nanomaterials, and nano-bio science and technology. Prior to returning to Australia, he directed the U.S. Department of Energy-funded Center for Nanophase Materials Sciences at Oak Ridge National Laboratory. Sean has published over 260 refereed journal papers with more than 15,000 citations. Welcome, Sean.
Hello, Gil.
I want to start with your recent essay in the special issue of the Journal of Advanced Theory and Simulations entitled Computational Materials Science, Discovering and Accelerating Future Technologies, in which you say moving the boundaries of knowledge, scientific research, and technologies forward through the field of computational material science requires a combination of fundamental understanding of materials properties and appreciation of the limitations with our current approaches and the ability to embrace new and emerging technologies. I have long felt, Sean, that research sort of lagged in materials sciences. We have been waiting for long, I think, for room temperature superconductivity, efficient photocatalytic materials, and others. So what do you mean by computational material science?
So computational materials science, Gil, can operate on different levels of detail, shall we say. My own field, coming out of theoretical chemistry and materials science, involves essentially bottom-up calculations from first principles quantum mechanics, and molecular dynamics approaches. And so we look at fundamental materials properties on an atomic scale, and then we infer we look for basically effective descriptors which are indicative for certain types of material behavior. And when we find them, we will pass that information to our experimental colleagues and suggest that they might try heading in that direction. There's another top-down approach that comes traditionally out of engineering, which works on macro scale and then tries to drive down using sort of more traditional finite element approaches. Equally sophisticated, but coming at it from a different angle. And I think that there used to be an enormous gap between these two different top-down and bottom-up approaches. And in fact, it's paralleled experimentally as well, by the way. But it's closing, and it's closing because of accumulated knowledge that's come out of the research sector. It's closing because of technological capabilities. I certainly saw that experimentally. I saw that when I was running the centre at Oak Ridge, because they were pushing the boundaries of atomic scale approaches, moving up towards micron scale, and then pushing down with the other more macro scale experimental approaches. And I've seen the same parallels going in terms of the ability of modeling to connect these bottom up and top down approaches.
Yeah. So when you say atomic scales, this is a bit like you have some kind of a target set of properties that you're pursuing, and then you're looking for this at the atomic scale. How exactly does it work?
So if I take an example out of catalysis, where my group's been very active in recent years, there's a lot of things you can calculate at the atomic scale. You can calculate a band gap for a material. Mm-hmm. You can calculate a chemical barrier for a particular reaction, which is thought to be a key step in a process.
Yeah.
And some of these quantities it's found are interesting, but not directly correlated to the actual catalytic function you're trying to develop, and others are found to be quite sensitive. And so when we talk about descriptors, we're really looking for key properties which seem to be quite sensitive in terms of the process you're trying to achieve.
Yeah.
And that has its own parallel, very obviously, in machine learning and AI, which are automated ways of finding these descriptor characteristics that are good signatures. And so once you've identified these types of characteristics, then you can go screening, doing calculations on many different potential materials and look at those properties. And that gives you indicators as to where you should push experimental work. Experiments are very expensive. And because the computer is getting more efficient, then we can help guide the process.
So you have an application in mind, let's say some kind of a catalyst, and there are some known catalysts out there. I'm just making the statement. Correct me if I'm wrong, Sean. So there are some known catalysts. They have some properties that you're already aware of. And those are sort of the initial conditions that you have, and that you're using it to try to find better and better materials. Is that a good way to think about it, or no?
I think that's a pretty decent way to think about it, Gil. Yes, and by using the theoretical calculations, we can often get a somewhat deeper understanding of what's driving the efficiency. And that gives us refined and sometimes somewhat better descriptors to go after, to try and chase.
Okay. And so that's where the machine learning comes in as well. So again, you have some historical observations, and as you run experiments at the atomic scale, you have some observations there, and perhaps machine learning on historical data might give you an indication, or maybe the probability that the new material or new properties could be useful in that direction.
I think so, and the thing is that the machine learning algorithms are, shall we say, as scientists, we tend to be a little bit tracked based on our past experience. Our thinking mode is kind of a little bit shaped in that way, whereas the machine comes at it without bias, and just works on the data that's available to it. And so there are advantages to that approach because it's an unbiased approach.
Right.
As long as the data set it's working on is unbiased, by the way, and that's an underlying issue.
Yeah. So, in life sciences, for example, high throughput screening, those types of approaches, when you have a target, you have a set of chemicals you're attempting, and sometimes a fully automated process where the machine is leading further experiments based on data generated appears to me more efficient. I would imagine this is an analogous situation here, right?
Yes, that's correct.
And so one of the areas that you have done a lot of work in is catalysis and hydrogen production. and using hydrogen as an energy medium as well as a storage of energy medium. Do you want to talk a bit about that?
Yes, so we're working on basically trying to find cheap and abundant materials which can be made active catalytically for hydrogen production.
Yeah.
And the overall scenario on that is that we would like to be able to use abundant sunlight to generate electricity through photovoltaics, obviously. And the issue then is if you want to do this on a scale that would lead to large-scale exports, because Australia has abundant sunlight, renewable energy sources, but how are you going to store amounts of electricity, amounts of energy on the scale of coal-fired power stations? This is way beyond what you could typically go buy a Tesla battery to store. Right. And we have some of the biggest batteries in the world down under here, but they don't go close to what you would need to do if you seriously wanted to replace coal-fired power stations and actually turn it into an energy export process. And so hydrogen is one of the solutions to this, because when you make hydrogen by splitting water, you use that electrical energy that you've harvested from the sunlight, and you use it to produce hydrogen as a fuel. And it's once you've made it, you can make it in any amount you want. The storage technologies are all very well established. And so it becomes an enormous energy reservoir, much like coal is today, right? Hydrogen basically replaces it as an enormous energy reservoir. Right. And then you can export it, you can use it domestically, you can use it as a fuel, you can burn it the same way you would natural gas, and it's a clean burning fuel, there's no carbon emissions. Or you can use it to turn back into electricity where you need it, using fuel cells. Yeah. So it's kind of almost a turnkey solution, which is growing in the perception of just how we could scale this out.
Yeah. So when you say make hydrogen from water, are we talking about the typical electrolysis or something different?
Yeah. No, that's exactly what it is.
So, okay. So you are using electrolysis to create hydrogen, but hydrogen you can store. And so I would imagine then you're talking about using solar energy production and then using that energy and basically converting that into a storage mechanism, which is hydrogen.
That's exactly right, Gil. Yes.
And so this is different from, I remember, sort of the 5th grade experiments where, we try to make hydrogen from water by just passing electricity through it. But that is an expensive way to make hydrogen, right? Clearly, the materials of the electrodes have a lot of impact on efficiency of that process. So this is another area that you have done a lot of work in.
That's right. So the materials that traditionally are used for that electrolysis process are precious metals like platinum. Yeah. And it's simply an expensive material. And so, yes, you can do it at moderate scale, but there again, if you're thinking about scaling this up to enormous scale, it just becomes an expensive bottleneck. And so a lot of the research that's being done, both theoretical and experimental, is attempting to find cheap and abundant materials which can perform at a similar level to platinum, and thereby will eliminate that particular bottleneck in the technology.
Okay, and so one of the things that you work with, it's actually carbon nanostructures. Is that?
That's right. Yes. Okay. Yes.
You want to talk a bit about that? So, and I know that you have a commercial company around that as well.
Yes, we do. So, in essence, we kind of came at this from left field, from a different direction to the sort of mainstream approaches, because we came at it from a theoretical perspective, and came up with an interesting idea about how you could potentially activate carbon materials to be effective for this electrolysis process, whereas usually they're not very good.
Yeah.
And it shows a lot of promise. So we've been proving up that technology at lab scale to see just how far you can push it, how well you can control it. But it's a novel and very interesting approach to using an abundantly cheap and available material, carbon, to replace platinum, essentially.
Yeah, so the savings there would be the electrodes, the materials of the electrodes themselves, platinum to carbon, but you still need the electricity, right? So the idea here, again, if you have some kind of a solar cell power power production somewhere, you could then attach to that this process that ultimately produces hydrogen, and the storage of hydrogen here, Sean, in at scale, how is the hydrogen stored in this case?
So yes, you've hit the nail on the head, Gil. That we definitely want to make hydrogen from sunlight, from renewable energy sources. That's really important because it means you don't have carbon emissions in doing so. I mean, the current high volume way to make hydrogen is from natural gas, essentially, by reforming, and that emits CO2. So it's not a terribly good way to do it. So we're looking at renewable energy, sunlight to electricity, which then makes your hydrogen from the water. And then the storage methodology, it varies depending on what your application is. The simplest way is to put it in a gas tank, and high pressure tank technology is well established and actually has taken great advances over the last decade or two. You can liquefy it. And in Australia, they're looking at liquefying hydrogen in order to ship it out to Japan at large scale as an export process. There are other ways you can do it. You can look for a solid absorbent material, and this has been a bit of a holy grail since way back in the mid-2000s decade, when there was a big push into hydrogen storage materials, and people were looking for materials which could absorb perhaps up to 7-8% of hydrogen, and then release it at sort of ambient pressures and temperatures when needed.
Yeah,
that's a tough target to achieve, in fact, and I don't think we've never really found an ideal solution to that. But there's still a lot of active work going on. Another interesting technology that is being developed at CSIRO, which is the sort of the national laboratory, if you will, down under here in Australia.
Yeah.
They're looking at ammonia. They're looking at ammonia as a vector for hydrogen, so that I think they've got a catalytic process which allows you to turn the hydrogen into ammonia effectively. And ammonia is naturally a liquid, so then you don't have to worry about low temperatures liquefaction of hydrogen. Ammonia is liquid at room temperature.
Right.
And again, transport methods for ammonia are pretty well established. So there's a few different ways you can go at this.
Yeah. I don't know a lot about it, Sean, but so the production of electricity is through some kind of solar based production, and so the advantages here in terms of hydrogen is both storage at scale and transportability of that source. And if you go to liquefying hydrogen and other transformation, then there's additional energy used there, right? And then transportation to, for example, Japan or something. So if you were to do that entire process, what would be sort of the total cost per unit of energy used ultimately?
I don't have a figure, a quantitative figure for that. It's being the cost and techno-economic analysis is being done in some significant detail, because there are pilot studies which are spinning up at the moment. But I think at the end of the day, it's the absolute cost. Well, yeah, it matters. But whether it's a viable export industry, at the end of the day, depends on how the cost of that stacks up against the attractiveness of being able to get hydrogen for the large Japanese and Asian industries.
Right.
And they don't have the same land space. They don't have the same. They don't have the available land space to do really large scale generation themselves, and often not the climate to match either.
Right.
And yet they're committed to transforming their economies to become carbon emission free. And so it's sort of a question of relative cost. How else are you going to get your hydrogen, basically?
Right. Yeah, it's almost like you have no other option.
Almost is. That's
Yeah.
right.
Yes, and if the energy were to be used locally, then I don't know what the efficiencies are for something like pump storage. But if you need to transport it, I would imagine just the conventional batteries like lithium ion or something like that. That would be just too expensive, I would imagine, right?
At scale, there's a tipping point with scale, and so typically for for household projects, for smaller scale things, or for example, okay, let me give you another example for that relates to the Supercomputing Center. We use batteries to back up our storage, okay, and the batteries will store enough energy to keep our storage active, and so if the power goes out, the batteries kick in, and they'll keep the storage active for long enough so that we can gracefully shut it down, on the order of 10, 15, 20 minutes or so, right? And so at that sort of scale, batteries are great. They work well. They're efficient. Even for Adelaide has what was the world's largest lithium-ion battery from Tesla, and they use it for intermittent power dropouts to stabilize the grid. But it can't run for a long time, and so it gets to a point where, at a certain scale, hydrogen takes over as being a more advantageous way to do it.
Right. Yeah. And I know that there are some developments, in the photocatalytic semiconductors, right, that does not require sort of running electricity through water, and then producing electricity using solar, and then running it through water.
That's right.
So where are we on that dimension, the photocatalytic dimension?
Yeah, look, it's one of these holy grail things. If I had a direct way to transform the sunlight and I shine it onto my catalyst, which is floating around in a slurry and water, and then off bubbles the hydrogen, that's it's very appealing, but it still essentially is, I would say, in the research domain, and so it becomes a question. If there's an imperative to advance this technology, then you're going to do it with components which are reasonably well established. And photovoltaics are now a very well established technology, and the cost scale's gone down. So at the moment, we would use the photovoltaics to get the electricity, and then we would do the electrolysis. But the direct route, which uses these photocatalysts, is very appealing if you can make it work, but still in research domain, I would say.
Yeah, so in the US, I haven't looked at the numbers recently, Sean. The photovoltaic solar cells still require, I believe, subsidies for them to make them viable. Is that the case in Australia? I mean, the production of
we
it.
don't. Yeah. We don't have, at least to my knowledge, and I'm not a direct specialist in the photovoltaic industry here down under. But my knowledge, the government is not pushing large-scale subsidies. What we're seeing here is that solar energy production is just taking off, and it's not something now that is actually driven by government subsidies. It's just taking off in enormous volumes.
Right. Yeah. And so, the goal has always been that once you get to certain scale, it becomes, sort of a self-sustaining. So it sounds
Yeah.
like Australia has already gotten there. I don't know if you followed this. Bill Gates, I believe, had invested in some sort of concentrating solar technology, which appears to be a lot more efficient for certain certain applications. I wonder,
Mm.
if you studied that, the concentrating solar aspects of it.
No, no, Gil, I have studied it, and I'm probably about as aware of it as you are. My understanding of it is relatively superficial, but I do know that, if you can use mirrors to concentrate solar energy, and then if you've got a material which can absorb that high intensity solar energy and store it in one way or another,
Yeah.
most likely as some sort of heat storage, then in certain cases that can be competitive.
Yeah, and the numbers I've seen is obviously it has applications only in specific areas, because you need to have,
Mm.
either you have to drive a turbine, to create the electricity, or you could use it in some sort of manufacturing context where you are using, some fossil fuel or electricity to melt things, things like that. But it requires obviously specific applications. So
Mm.
the product that you have, Sean, is that is an industrial scale product, right? That you're pursuing with the company. What's the company called?
Caltech.
Caltech. Yeah.
Yes, it's Caltech. If the technology works, then it will scale out to an industrial scale very directly because the material is so cheap and so available. But we're still proving it up out of the lab scale to make sure that it's efficient and it's controllable, and we know how to engineer it for scaling into industrial settings. So our technology is still pre-industrial scale, and we're basically proving it up.
Do you expect some sort of domestic application? I know that hydrogen is not easy to handle, but do you foresee any sort of small scale domestic application, residential, I should say, application?
Yeah, that's right. These experiments are these sort of pilot studies are developing here in Australia, I suppose in the States too. I don't know, but we are looking at it because, and when I say we, I don't mean Cheltec in that context. I mean the Australian sort of sector.
Yeah.
They're looking at pilot studies because the first step in this is that you can bleed hydrogen into a natural gas network.
Mm.
Up to, I think it's figured they can bring it up to about 20%, or close to that anyway.
Mm.
And it still burns like natural gas, and yet it's a certain percentage of hydrogen.
Right.
And so in the first pilot studies, they're looking at producing hydrogen from solar and then bleeding it into the natural gas network to get a handle on the technology basically first.
Yeah.
But it doesn't then require that they completely change the gas network. If they were to flip to 100% hydrogen going through the gas infrastructure, then you've got to change your burners basically, and do some other changes. And so the first step is to actually bleed it into the natural gas network. Now, if you then think about, and that's at suburban scale, right?
Yeah.
If you think about a household, ordinarily you would you'd have a Tesla battery on the side of the wall basically to store a certain amount of energy.
Yeah.
And that at a household scale that works pretty well. And so the question is, well, normally we think hydrogen takes over as being more effective at large scale. Would it have a utilization at a household scale? This actually, it might, if you can eliminate certain parts of the process. So if you've got your solar panels on the roof, you turn that into electricity, you turn that into hydrogen, you take a hit right there.
Mm.
And then when you want to turn the hydrogen back into electricity again to use it, you take another hit.
Right.
And so if you can find a way to eliminate some parts of that, then it may become competitive at household scale. So for example,
Yeah.
what if I make the hydrogen And then I just bleed it back out into the gas network, and I get a discount on my gas bill, because I've produced hydrogen and fed it into the network, right?
Yeah. Yeah.
We already do this for electricity. You might be able to do it for hydrogen as well. That eliminates one part of the cost factor. So there might be ways that it becomes relevant at household scale.
Yeah, but if you have solar panels on the roof and you are on the grid, I would imagine the most efficient way to provide that excess energy back would be through electricity, right? If you convert back into hydrogen, yeah, as you say, you
Well,
take a hit there, right?
yeah, no, I know what you mean, Gil. However,
Yeah.
this then again comes back to the capacity of the grid to
Right.
take
Right.
that electricity.
Right.
And for example, here in Canberra, the electricity suppliers are at a point where they're actually trying to they're trying to tell new suburbs not to build heaps and heaps of solar,
Mm.
because what happens is at the middle of the day you get a flood of electricity pushing back onto the grid, and they don't know how to deal with it. It comes back to storage again,
Yeah.
right?
Yeah.
So there are issues with that too, in fact.
Yeah. So I mean, if you're practicing dynamic pricing of some sort, then you will be driving down prices to probably close to zero.
They go negative. That's
Yeah,
right.
or to negative, because there is no way to store it. So the beauty of hydrogen there is really its ability to store energy and
Exactly.
and release it as
Exactly.
necessary. While you were
Yeah.
talking, Sean, I was also thinking, if you were to put that into the natural gas grid, what is the
Mm.
mechanics of this thing burning? I would so the natural gas produces CO2, hydrogen when it burns produces water, right?
Mm. That's right.
So how does it work in the in the kind of a typical burner?
So I think, and look, I'm not an engineer in that sense, skill,
Yeah.
so I can't make authoritative observations on it. But my understanding is that up to the order of maybe 15 to 20% of hydrogen,
Mm.
you can actually burn it through the traditional gas top elements or whatever, and it works fine. It doesn't produce any real difficulties.
Okay.
However, if you're going to go above that, you are going to need to redesign your burner, and so you'll need to swap out the elements and so on.
Right. Right. And so
I should imagine that
yeah.
they'd have to have some way, surely, of absorbing excess water. I mean, you
Mm.
might end up with a lot of vapor around the house and getting mold on the walls or something. There's got to be something you've got to do, right?
Yeah. Yeah. The interesting thing about this is that conceivably, if you look forward, you say we want to get out of all fossil fuels, but there is an infrastructure already in place for natural gas, and
Mm,
we could that is stranded investment. So we could use the
exactly.
same infrastructure, but this time it's going to take hydrogen. So essentially, you eliminate
Yeah.
all greenhouse gas issues, but still use the infrastructure that's already in place.
That's I mean that's the game insofar as the utilities companies are concerned. They've got billions of dollars of investment in the gas network, and if they can repurpose that relatively seamlessly to hydrogen without having to build a new network, that's a big win.
It's a great
Um,
win, yeah.
and just getting back to our earlier point around the negative pricing during the daytime when all the electricity is coming back out of the rooftop solar panels,
Yeah.
the electricity suppliers are looking again at hydrogen as a way to stabilize the grid. So when they have all the electricity flooding onto the grid,
Mm.
they actually could use that to make hydrogen to store it. And so it's a stabilizing mechanism in that sense, as far as they're concerned.
Right, right. And you mentioned ammonia. So what's the mechanism there?
I actually don't know. I just know that the CSIRO have got IP which they're working on,
Okay.
which is, I think, a catalytic process for going to ammonia instead of hydrogen. And that's about as much as I know.
Okay. Okay. Yeah. I mean, if you look at a country like Australia, southwestern part of the US, perhaps India, these are places where there is abundant solar energy, and it hasn't really been utilized in some efficient fashion. And I think the push has always been solar panels, which in the US, as far as I know, is still not sufficiently viable. It requires a subsidy. But perhaps, the issue there is, just like you say, it produces excess energy at some point, but it doesn't at other points. And so the pricing that you can command on that infrastructure is highly variable, and that goes into the economic equation. So if you have a modality that allows storage, that whole equation changes quite dramatically.
I think that's a good comment, Gil. Yes.
Yeah, so you are
And I
working
know.
on, sorry, very quickly, Sean. So you're also working, so based on what you said, it could be distributed storage, or the electricity company itself saying, we are going to get excess power in these hours of the day. We can efficiently store it, right, at a central location as well.
That's right. That's correct. Yes.
Sorry, you were saying something. I interrupted you.
No, I noticed recently that Saudi Arabia apparently is making a big push for solar and renewable energy. It's part of their vision for ultimately transitioning out of fossil fuels.
Yeah, I mean, I don't know, exactly what path we are on, but I think once the population start to see the real effects of a temperature rise, really
Yeah.
affecting their lives. London today, I think, is at have 90 degrees or something like that. It's hotter than southeastern part of the U.S. today.
Yeah.
So I think once the larger population start to see the effects, I think it's going to come back to the policymakers to move on it a lot faster than they have been.
Yeah. Tell me about it, Gil. You know what we went through last summer down under here in Australia.
Yeah.
It was just it was appalling, and the whole country was just aghast at the bushfire season we had.
All right. Yeah. I
So
remember. Yeah.
yeah, it was a groundswell and changed a lot of political thinking and motivations down here.
Yeah. So in conclusion, Sean, I know that you're working on a lot of this research ideas, but also on the practical side of applying it. If you look forward, say 5 years, where do you see we would make the biggest leaps, both in terms of research as well as applications?
Well, I think, Gil, we are going to find one of the enormous objectives which we're progressing towards is basically this transition out of fossil fuels and into renewable energy, which requires the storage equation to be solved.
Yeah.
We will find abundant catalysts to do this, which will make that entire chain. It'll make it economically viable and scalable, and for Australia, it's going to turn into an enormous energy export market, which ultimately will replace Australia exporting coal, which is really important. So that's a big thing. Likewise, we're dealing with demands in the biotech sector, which are accelerating too. With the obvious example we deal with currently globally, the COVID-19, and the methods by which we're accelerating our ability to combat these things are advancing dramatically, and that is in no small part underpinned by compute and modeling. And so the advances in computational capacity and our ability to move ahead of experiments and find avenues that they can follow is completely changing the way in which research gets done and the way these advances are made. And I think that is a game changer as well going forwards.
Yeah, I mean, it's really exciting times. Material sciences, the way that you are doing some of this, let's call it discoveries, kind of bottom up discoveries at the atomic scale, could have a huge impact, right? Material sciences, as you mentioned, I would imagine has been largely a top-down process, looking for new materials and then looking for a property. But now you could actually seek the property or predict the property and have designs that sort of bottom up, right?
Yes, and this conception, it's not. It's been around for some time. The whole materials genome initiative out of the US was based on this precept.
Yeah.
And it's a great idea, but it's not easy. But it's accelerating, and I think we are starting to see that kind of process really kick goals now, after a decade really of spinning it up.
Right, right. Yeah, excellent. Yeah, so this has been great, Sean. I really appreciate the time that you spend with me, and good luck with
Well, thanks,
all
Gil.
your
I
research.
really enjoyed it too. Yeah, it's good talking to you.
Yeah, thanks so much. Bye.
Okay. Thanks then. Bye-bye.